potential example, let's take a charged rod of length L where the charge is uniformly distributed. What is the electric potential at a point P, which is a distance y, above one end of the rod? So we're no longer in the center, we're off at one end, and we want to find the total potential. So the first thing we do is we identify a little bit of charge dq on our rod. There's our little bit of charge dq. We know that dq makes a potential, which we call dv. That's at point P. So let's write down what our dv is. So dv, the little bit of potential at point P due to dq, is k times dq over r. And let's make sure we know what r is. R is the distance from our charge to our point. So from here to here, there's the r value. How else are we going to write down r? We see that r is the hypotenuse of a right-angled triangle. Let's get a coordinate system on there. So let's put our y-axis here. So there's y. And let's put our x-axis along here, going right through the center of that rod. There's our x-axis. So the distance from our point P horizontally to our charge is x. So that means r is equal to the square root of x squared plus y squared. So there's a value for r. So to get our total potential at point P, we have to do the integral of all of our potentials. We have to add up all of the potentials. And let's see what we're going to write down for that guy. So our dv is k times dq over r. R is equal to k times dq x squared plus y squared. So our total potential is going to depend on x. So x is the thing that varies because we're adding up the potential due to all these little bits of charge which are moving along in the x-axis. That means we'd like to be able to write our dq in terms of x. Let's think about what is dq. So dq is a charge, and the size of that charge, dq, is going to be the charge density times the length. Now the length, it's a little bit in the x direction, it's a little bit in the horizontal, so the length is dx, and charge density is what we call lambda. So charge density can also be found as q over L. So let's fill this in up here. So we get k times lambda times dx divided by the square root of x squared plus y squared. So we identified our dq, we wrote down our dv, and we filled in what we knew for dv. Now to find our total potential, we add up all the pieces. To add up all the pieces means do the integral over dv. So let's fill that in. K lambda dx over square root x squared plus y squared. I'm going to do the integral, so we need to have limits. We have to add up along the entire length of the rod. So let's start at this end and let's go all the way along, add up all those contributions until we get to that end. So here our rod starts at x equals 0, x initial equals 0, and it finishes at x final equals L. So we'll take our constants out front, k and lambda, integral from 0 to L, dx over square root of x squared plus y squared. If you want to do the integral, you can go ahead and do it, or you can just look it up in a book. So we get k times lambda times the natural log of x plus the square root of x squared plus y squared. That's going to be evaluated at L and 0. To do that evaluation, we get k times lambda times the natural log of L plus square root of L squared plus y squared. And then we take away natural log of, put in x equals 0, square root of 0 squared plus y squared. That, of course, is just going to be y, that whole thing. And you might remember the identity that natural log of 2 natural logs subtracted is the same as the natural log of the arguments divided. So that would be k times lambda times the natural log of this guy, L plus L squared plus y squared, divided by this guy, which is just y. So there's the result for the potential above one end of a rod.